Imagine blinking, and in that fraction of a second, you just lost $5 million.
Yeah, it's brutal.
Right. But, I mean, that is the reality of high-frequency trading. So, welcome to the deep dive. Today, we are looking at the stack of sources you sent us on Aeron, which is this open-source messaging backbone.
And it's huge in this space.
Oh, absolutely. It basically keeps dozens of high-frequency trading firms and exchanges from just, well, crashing under the weight of, like, 20 million messages per second.
Which is a staggering amount of data to process.
It really is. So our mission today is to figure out how software can possibly move that fast and, what breaks when you push it to the absolute limit.
Well, the thing is, when you were dealing with 20 million messages every second, standard networking protocols completely collapse.
They just can't handle it.
Exactly. You have to totally rethink how data physically moves between applications. And Aeron does this by shifting the paradigm with something called a media driver.
Okay, so looking at your notes, the easiest way to picture this media driver is like having a dedicated postal sorting hub built directly inside your house.
That's a great way to think about it.
Right, because instead of walking a letter out to a mailbox on the street, your applications just drop messages directly into a shared space on the same machine.
Yeah, and that shared space relies on memory-mapped files located directly in the system's RAM.
Okay.
But the real magic is how they manage traffic in that space without applications colliding into each other. They use a triple buffered append-only log.
Wait, what does that mean in practice?
Basically, while one buffer is actively being written to, a second one is being read, and a third is being cleaned.
Ah, so nobody has to pause and wait for a file to unlock. Readers and writers never actually bump into each other.
Right. They just use these atomic position counters to instantly track who is where in the log.
Which explains how the interprocess communication round-trip time drops to, roughly 250 nanoseconds. Because you are completely bypassing the operating system's networking stack for local communication.
Exactly. It drastically beats general-purpose messaging, especially on tail latency, because there's virtually zero wait time.
But okay, here is my hang-up with all this. Raw speed is great. But in capital markets, losing a single order is a disaster.
Oh, it's catastrophic.
Right. So if you force the system to stop and guarantee that every single message was safely recorded, doesn't that inherently destroy that beautiful 250 nanosecond speed?
What it absolutely would, yeah. Which is why Aeron makes reliability modular.
You pick and choose.
Exactly. You don't pay a speed penalty on the critical path if you don't need to. Like if you just need a paper trail for regulatory audits, you use their archive component.
And that just quietly records streams to a disk in the background, right?
Yeah, without slowing down the main traffic.
But if you need a bulletproof guarantee that no message is lost across multiple machines, your sources mention the cluster component, which relies on Raft consensus.
Right, which forces a strict majority of servers to vote and agree that a message is safely saved before they move on.
Which obviously adds latency.
It does, but it gives you absolute fault tolerance. There's even a newer closed source component from 2025 called the sequencer.
Oh, right, the one that creates a single global timeline of events.
Yeah, to guarantee absolute fairness across different trading venues.
Okay, all this modularity makes sense, but I mean, I'm looking at a glaring contradiction in these notes.
The Java issue.
Yes, Aeron is written in Java, and Java runs on the JVM, which is notorious for garbage collection, meaning the system will literally just freeze for a moment to clean up memory.
It's the ultimate elephant in the room for HFT.
If we are counting nanoseconds, a JVM pause is basically an eternity.
It really is. When the JVM hits a safe point to clean up memory, your 250 nanosecond latency can unpredictably spike to milliseconds.
Which is unacceptable in this field.
Yeah. And another major bottleneck in the open source version is the lack of zero-copy networking.
Meaning the CPU can't just let the network card place data directly where it needs to go.
Right. The CPU actually has to waste precious cycles manually copying data from the network socket into the application's memory.
And that manual copying introduces critical drag.
Exactly. And remember that centralized sorting hub we discussed?
The media driver.
Yeah. Because every single message must physically route through it. That extra shared memory hop eventually becomes a physical bottleneck when you scale up to massive extremes.
But the very architecture that makes it fast early on becomes a thing holding it back at scale.
Which is exactly why a new generation of challengers is emerging to address these exact flaws.
Like Chronicle Q, right. Though that one is still Java-based, heavily used, but wrestling with those same garbage collection ghosts.
Yeah, but then there are newer challengers like ZigBolt.
Written in a low-level language called Zig.
Exactly. It fundamentally sidesteps Java's overhead. We are talking boasting 20 nanosecond latency with zero garbage collection
I go
pauses.
from 250 nanoseconds down to 20 nanoseconds just by ditching Java.
It's a massive leap.
It really is. And it leaves you with an interesting thought to mull over for your own projects. As trading systems abandon traditional languages for ultra-low-level ones just to shave off fractions of a microsecond.
It makes you wonder where the ceiling is.
Exactly. At what point does the physical limit of our hardware completely dictate the software we're even allowed to write?